because of the relation to functional analysis that I'll talk about later. So we'll just stick to the simpler case of one Wasserstein distance. Okay, so here's what a coupling looks like. So you imagine kind of in this case, let's say you have one-dimensional distributions of mass on the X and Y axis. So a coupling is kind of, I've kind of drawn it like a topographic map. So you can imagine that if you sort of shine a flashlight down on this this mountain system, you'll get the blue distribution, and if you shine a flashlight right, the shadow that you cast will be this red distribution. So that's this marginal condition where you're saying, you know, if you project down onto the first and second coordinate, you should get the measures that you started with. And then you can imagine that at a single point, that's sort of telling you it's indicating the infinitesimal amount of work it takes to move this point of mass here on the x-axis to sort of this point of mass here on the y-axis. So it's known that for sums of Dirac delta, so discrete measures, the optimal transport is just equivalent to the assignment problem. So basically find a perfect matching with minimal cost. And then in that case, then a coupling itself is discrete. So a coupling is just going to be a discrete measure on the product space, and each Dirac delta is just saying, okay, match, you know, this point to this point on the y-axis. And we can also split mass. So for instance, if we have a mass, if we have a Dirac delta of mass 2, we might want to match that with 2 points, 2 Dirac deltas on the x-axis with mass 1, for instance. But the coupling itself, the optimal coupling, can always be chosen to be a discrete measure like this. Okay, so what's the problem for us? And in the case of persistence diagrams in particular, so this doesn't work if our pile of gravel and our hole don't have the same volume. So here I have a tiny little hole, can't get the gravel there. So in this case, the Wasserstein distance is undefined, or you could just say it's infinite. Okay, so then that's where we're going to introduce relative optimal transport. And so I should say that, yeah, again, this idea has been introduced, at least in the setting of Euclidean Euclidean space, measures on Euclidean space by Figali and Geely. So they studied measures supported on a bounded subset of Euclidean space, and in that case, you're allowed to match the boundary. And then Divol and Lacombe extended this to measures on unbounded open subsets of Euclidean space. So we're just going to consider general metric spaces. So suppose I have two measures mu and nu on some metric space X. And now suppose that mu and nu don't have the same total mass. So let's say mu has more mass. So how can we possibly match these measures? Well, suppose we have some subset A, which we designate as sort of an infinite reservoir of mass. So in that case, what we could do is, well, for instance, we could just move all the mass of mu over to nu, and then whatever's left over, we could just borrow from A. Of course, that might not be super efficient because, for instance, there's some mass over here that I could push to A and then pull out over here and send to nu. So for example, yeah, so maybe some measure over here, some mass over here, I send to mu or nu, and then this part over here that's really close to A, I send to A, and then I take a little bit of extra mass from A and send that to nu. And I guess one way of seeing that would be that we can take shortcuts through A. So think of A as sort of being a place where it's free to transport mass. So I can always take shortcuts through A if I want. So let me formulate this in a way that resembles the Kantorovich formulation of classical optimal transport. So some quick setup. So suppose we're always supposing that we start with a pointed metric space. So imagine in this case, instead of looking at the subset A, it's just a single point. We can always pass to this situation by taking a quotient space. So just for simplicity, we'll assume that our infinite reservoir of mass is concentrated at a single point, x naught. So m plus of x is just the monoid of positive radon measures on x. So radon measures are just measures that are sufficiently regular that kind of are compatible with the topological structure or the metric structure. And then we're going to look at the quotient monoid. So this is sort of motivated by what we were doing before, where we were defining persistence diagrams as quotient monoids. We'll do the same thing here. So we'll just look at radon measures modulo mass at the base point. Okay, so really what this is we're just defining a congruence relation on the monoid of radon measures. So we're saying that mu is congruent to nu if I can just add some mass at the base point to mu and to nu, and I get the same measure. So basically, another way of saying this is that these measures are equivalent off the base point. So if you restrict to the complement of the base point, you get the same measure. So integration is well defined on these equivalence classes, as long as you're integrating against functions which vanish at the base point. And so we'll look at this submonoid of all mu which have finite total distance to the base point. So you're just saying that if you integrate the distance at the base point, you want to get something finite, and that's just going to ensure that what we get is actually a metric. And now, so here's the formulation. So suppose we have two of these measures mu and nu, and so just to be clear, so when I look at mu and nu, really I'm looking at an equivalence class of measures mu, or of a measure mu. But all you have to think is when I look at a measure mu, I'm just considering that measure up to possibly some adding or subtracting some mass at the base point. So a coupling in this situation between mu and nu is again a measure on the product space, such that the first and second marginals now are not required to be equal to mu and nu, but are just required to be equivalent to mu and nu. So basically, this is the exact same formulation as the classical Kantorovich formulation, except I'm relaxing my notion of equality. So then what we're calling the relative one Wasserstein distance is just defined to be the infimum of the cost of a coupling taken over all couplings. So this is exactly the same definition of the cost in the classical case. So really all we've done here is just relax our notion of equality. So just relax the marginal constraints. And so we also get a norm. So I could define the one norm of one of these measures, one of these equivalence classes of measures, as just the relative one Wasserstein distance from mu to the zero measure. Okay, so it's almost, deceptively simple. So let me do an example just to see how sort of these marginal conditions play out. So suppose that mu is a Dirac centered at some point y, and nu is 2 times a Dirac centered at z. Okay, so it's a Dirac with mass 2. So y and z are distinct points, and they're distinct from the base point. So what would be a matching here? Well, one way of doing this, of course, would just be to send the 1 unit of mass at y to the base point, and then borrow the 2 units of mass from the base point and send those to z. Okay, so the cost of this would be the distance from y to the base point plus 2 times the distance from z to the base point. Of course, this is not a very good matching because of the triangle inequality. So in particular, I sent some mass to from y to x naught, and then I sent some mass from x naught to z. I could have just sent that mass directly from y to z, and that cost by the triangle inequality would have been less. So a better matching would be to send 1 unit of mass to z and then borrow the remaining unit of mass to x naught. And so I claim that this is actually the optimal coupling. So let's just see what the marginal constraints look like. So the corresponding coupling there is just a discrete measure on the product space. And basically it's just saying match y to z and match x naught to z. Okay, so if we project onto the first coordinate, we get delta y plus delta x naught. So again, this is not equal to mu, but it is equivalent to mu, right? So this is sort of where this weakening comes in, is that we didn't get something that's dead on mu, but it's still equivalent to mu or congruent to mu. And then the second marginal turns out to be nu on the nose. And now if you look at the cost of this coupling is exactly the distance from y to z plus the distance of z to x naught. And so the relative one Wasserstein distance is at most this quantity. And you can actually check that this is optimal. It's not too hard to check, but I'll skip that for time. Yeah, so this is the optimal coupling. So this actually gives us the one Wasserstein distance. Okay. So the reason I'm considering the one Wasserstein distance in particular is one, because well, Figali and Gigli studied the p=2 case in the context of heat equations and gradient flows. So what we noticed is that, at least for the one Wasserstein distance, there's a close connection to functional analysis on spaces of Lipschitz functions, which I think is really interesting. So the setup here is, so again, we're looking at a pointed metric space. And just for simplicity, we'll assume we have a compact pointed metric space. So Lip x dx naught, this is the vector space of all real valued Lipschitz functions which vanish at the base point. And Lipschitz functions have Lipschitz constants. So f lip norm is just the smallest Lipschitz constant of f. And this space actually is a Banach space. And so one really interesting thing that we noticed right away is that there's sort of a representation theorem. So these measures, or these equivalence classes of measures, are actually in one-to-one correspondence with linear functionals on the space of Lipschitz functions. Okay, so let me say that more carefully. So suppose we have a bounded positive linear functional on this Banach space of Lipschitz functions, which vanishes at a base point. Then there exists a unique mu in this quotient space, so that, excuse me, I is just given by integration against mu. So I guess just to be clear again, when I say a unique mu, basically I'm saying there's a unique mu modulo that equivalence relation, right? Moreover, so the operator norm of this positive linear functional is actually equal to the Wasserstein norm. So essentially what we're saying then, so these things are semi-vector spaces, in the sense that if you look at the space of measures, you can add two positive measures and get a positive measure, and you can multiply by a positive constant and get a positive measure. So that constitutes a semi-vector space. And then this one Wasserstein norm is a norm on that semi-vector space. So the object you get is a normed semi-vector space. And so this theorem is saying that the normed semi-vector space of positive Radon measures is isometrically isomorphic to this space of bounded positive linear functionals on Lipschitz functions with the operator norm. Okay, so this corollary is really powerful and useful. I mean, we proved a lot of things with it. So, I mean, one thing in particular that's really simple is that if you have two of these measures, these are equivalent if and only if they agree when you integrate any Lipschitz function against them. So integrate for any Lipschitz function which vanished at the base point, integrate against mu and nu. If you get the same thing for all f, then those measures were actually the same measure in this quotient space. So in general, we proved a lot of analogs of classical results in this setting. So another one is Kantorovich-Rubinstein duality, which gives a dual definition of the one Wasserstein distance. So that says that the one Wasserstein distance between mu and nu, you can actually compute instead by looking at all one Lipschitz functions which vanish at the base point, integrate mu and nu against those and take a difference and take the supremum of that quantity over all such one Lipschitz functions. But what is this right here? So this is really just the operator norm. So if we view mu and nu as linear functionals on the space of Lipschitz functions, then Kantorovich-Rubinstein duality is just saying that the one Wasserstein distance between mu and nu is precisely the distance induced by the operator norm. So another thing we considered is weak convergence. So essentially what we're saying here is that the dual space, in some sense, it's not quite the dual space because we're looking at the positive version. So let's say the semi-dual space of the space of Lipschitz functions is the space of measures. And so it sort of makes sense to define weak convergence or vague convergence as convergence against Lipschitz functions. In this case, the weak and the vague convergence coincide. So I'll just say that mu sub n converges weakly to a measure mu if when you integrate against a function, a Lipschitz function f, that integral converges to the integral of f against mu for all Lipschitz functions. And so we'll write, mu sub n converges weakly to mu with this little w over the arrow. And so a theorem analogous to a classical theorem is that weak convergence is the topology of weak convergence is metrized by the one Wasserstein distance, or in this case, the relative one Wasserstein distance. Okay, so mu n converges to mu weakly if and only if the Wasserstein distance goes to 0. Okay, and then this was kind of what motivated us to actually look in this direction. So for persistence diagrams, we had a universality result, which I didn't mention for the sake of time. So let me mention the analogous result here. So this construction is universal in the following sense. So if you start with a pointed metric space, there's a map delta, which basically just sends a point to delta x, to its Dirac delta. So the measure just 1 unit of mass concentrated at x. But of course, the base point gets sent to 0 because in this quotient space, x naught, the Dirac at x naught is just the 0 measure up to equivalence. So this is a pointed map into the semi-metric space, a semi-vector space. Now, suppose we have another, I guess I also didn't mention that this space is complete. Okay, so suppose we have another complete norm semi-vector space, n, and we have a Lipschitz function into that space. So then there exists a unique extension of phi, so to this capital phi, which is going to be a positive linear functional, so that this diagram commutes. So another way of saying this is that you have this functor from pointed metric spaces into complete semi-vector spaces, complete norm semi-vector spaces, and it's universal in the sense that it's the left adjoint to the forgetful functor going the other way. Okay, so this construction is universal. So I guess another way of saying that is that this space is the free complete norm semi-vector space on a pointed metric space. Okay, so that's kind of abstract. I guess one corollary is a characterization of the relative one Wasserstein distance. So it turns out that this is the largest complete translation invariant homogeneous metric for which this delta function is an isometric embedding. So in other words, if we have another metric on the space of measures, which is complete, translation invariant, that just means if I do mu plus gamma, nu plus gamma, take the distance, that's the same as the distance between mu and nu. Homogeneous just means that I can multiply by positive constants. I can pull that out. And then isometric embedding just means that the distance between the Dirac center at x and y are just the same as the original metric that you started with. So if rho is a metric that satisfies all those things, then it's less than or equal to the one relative Wasserstein distance. So this gives a complete characterization of the one Wasserstein distance. So that's really cool. I think sort of what's going to be really interesting maybe in practice is kind of a dual version of this theorem. So suppose instead that you have a linear function on measures themselves. So you're going from the semi-vector space of measures, you have a positive, or let's just say a linear functional. Then there exists actually in this case a unique Lipschitz function, so that, if I want to take I of mu, that's the same as integrating f against mu, and this has to hold for all mu. So this is the dual situation to what we were considering before. Before we said that there was a unique measure that gave you that linear functional. Now we're saying there's a unique Lipschitz function that gives you this linear functional. And moreover, this Lipschitz constant, the Lipschitz constant of this function f will be equal to the operator norm. So I guess a corollary, so instead, let's say we have a linear map into Euclidean space. Well, then if we just project onto the components and apply this theorem, we get a unique sequence of Lipschitz functions, so that I is given against by integration in each component against these Lipschitz functions. And even more generally, suppose we have a linear function into a Hilbert space, which is separable. So then we can, any separable Hilbert space has a countable orthonormal basis. So we can project onto each coordinate of this orthonormal basis and apply the same thing. So now we get a sequence of Lipschitz functions, so that I is given component-wise by integration against Fn for all mu. So why do I think this might be useful? So this theorem here is, so a lot of people are interested, of course, I am too, in linearizations of persistence diagrams. So persistence diagrams sit inside this space of measures. So if we want to map persistence diagrams into, say, a Hilbert space, this theorem is saying it suffices to pick a collection of Lipschitz functions, so some sequence of Lipschitz functions, then any linear map from the space of diagrams or the space of measures more generally is given by integration against these Lipschitz functions. So in other words, in order to find interesting linearizations, we might try to seek out nice classes of Lipschitz functions which define these linear maps. Okay, so this is like sort of like template functions, so choosing nice functions that give you nice linearizations. So this has been considered before. I think this gives a nice theoretical justification for trying to do that. And so this is what we're working on now, and I think this could be potentially useful. So that's all I had, so thank you.
Thank you, Alex.
Yeah.
Any questions? Yeah, Luis, go ahead.
Hey, thank you for the talk. Very interesting. So I have maybe two questions. One is this related to the work by Kevin? I think it's Kevin Guittet. I'm probably mispronouncing that, but there's like a paper from 2006, I think, about Kantorovich norms where like you're allowed to, well, they have the same problem where like the negative part and the positive part don't really match, and you're allowed to like throw away some stuff.
Mm-hmm.
And
yeah, so yeah, so I don't know that particular paper. Maybe you could send that to me. But yeah, so there's a bunch of different ways of doing this. So there's something called partial optimal transport, where again you're allowed to throw away mass. Then there's unbalanced optimal transport, where sort of you're allowed to increase the size of particles as you move them, but at some cost. So they're not quite the same, but they are related. And I think, one of the things I want to do is write down a direct comparison. So how are they related exactly? Yeah.
Right. Yeah, because there seem to be many ways of doing similar things, and I'm just wondering, because you seem to be like, you have like a pretty clear setup, so maybe it would be like a good way to relate all these different notions that, as you said, were like usually phrased only for like Euclidean spaces, and maybe it's harder to see what's happening there, but in this like more abstract setting, it's easier. I don't know.
Yeah. I appreciate the reference. Thank you.
My other question is about sine versions of this, and in particular, if there is some way of not being forced to use the one Wasserstein distance and use like an infinity one, I would like that.
Yeah, so I mean, from what I know about this, working on signed versions of stuff, yeah. So I mean, the one Wasserstein distance is the one that works because it's translation invariant. And so if you want to extend to the sign setting, you need some sort of translation invariance. I mean, what does work is if you have a very strong notion of triangle inequality on your underlying metric.
Mhm.
So if your metric is a p metric, so it satisfies the distance between 2 points is less than or equal to a p norm version of the distance to a third point, then you can do this. But in general, I mean, I don't know. I think translation invariance is really important to be able to extend it in sort of a canonical way.
Right. I mean,
I think
that's
we
kind of,
should-
yeah,
No,
sorry.
I think we should go
Yeah.
move on to the next speaker.
Yeah, sorry.
So let me start recording.